wonder of flight has puzzled mankind since prehistoric times, when nature first started to solve the problem of flight. After untold millions of years, nature evolved the earliest forms of flying creatures, such as the grotesque pterodactyl and the first feathered bird, the Archaeopteryx, which were flying before ever man roamed the face of the earth. Nature's development of flying creatures has taken many millions of years, and today we have the eagle with its slotted wingtip feathers for slow landing. But even nature failed to make wings strong enough to carry on the evolution to the high-speed flight of today. To mankind, in a mere 50 years, it was left to advance from the eagle's counterpart, the glider, by way of the stick and string biplane, to the near-sonic crescent-winged aircraft of today. Aircraft like the aptly named Victor, shielded by the sound barrier against the onslaught of fighters. How has this rapid advance taken place? Not by slow natural evolution or the survival of the fittest, but by scientific research and practical development. In design offices, aerodynamicists, stressmen and designers think years ahead and evolve the aircraft of the future. In wind tunnels, technicians test models of aircraft yet unveiled. In the works, too, modern methods of construction have played their part. Machining of metal skins is only one of the new techniques in use today. All these have played their part in the latest development for high-speed, long-range flight, the Crescent wing. On airfields, the work of engineers, test pilots, and flight observers has proved the quality of this new wing form. Why was it evolved? What are its advantages? The wing is, of course, the vital factor if we are to fly fast and far. Here we must look at a little bit of theory and study the airflow in model form. For high speed, it must have a low resistance, or drag, and not set up shock waves as it moves through the air. Equally, to fly far, it must have large span. Here in a smoke tunnel, we see a model wing. The white smoke streamlines show how the air flows round it. One reason for drag is that the wing, moving through the air, drags along a thin layer of air with it. And eventually eddies are set up around the wing, just like the water eddies you see along the side of a ship. This air, moving with the wing, is known as the boundary layer. The boundary layer, which is thin near the leading edge of the wing and becomes thicker towards the trailing edge, eventually separates from the wing surface and eddies are formed. This eddying mass of air forces apart the steady airflow surrounding the wing and causes the type of drag known as form drag. So long as an aircraft flies well below the speed of sound, its wing causes the air to divide above and below it as smoothly as the Red Sea did for Moses. This is shown by this view of a wing section in a wind tunnel. As the aircraft's speed increases, however, and nears the speed of sound, a point is reached at which the aeroplane starts shock waves in the air. These shock wave disturbances, when photographed, appear on the screen as black bands on either side of the wing section. In effect, the aeroplane moves so fast that it starts to compress the air near it. This produces disturbances which greatly increase wing drag. These compressibility effects are first felt where the air flows most rapidly over the wing, that is, at its thickest point. If the wing is thick, the air has to speed up on going around much more than if the wing is thin. The thinner the wing, that is to say, the thinner it is in relation to its width, or chord, the less the divergence of the streamlines, and the less the increase in speed at which air will flow past the aerofoil's thickest point. We can see what happens to the airflow around a thick and a thin wing when they're placed in a high-speed wind tunnel. The airspeed is increased. The shock waves are formed first on the thick wing section and appear as black bands on the screen. When the speed of the air in the tunnel is increased sufficiently, shock waves begin to be formed, black bands to appear on the thinner wing. But the thinner the wing, the longer will the onset of the shock waves be delayed. When the whole aircraft is flying at the speed of sound, shock waves form at the leading edge of the wing. Shock waves and the turbulence they cause are responsible for the immense increase in drag when the aircraft flies near the brink of the sonic barrier. This shows that a thin-winged aircraft can fly much faster than a thick-winged one before it is affected by shock wave disturbances. Much of the shock wave arises from a badly designed wing. We must avoid all rapid changes in section or any projection. This is why the wing is so vital a factor in flight at high subsonic speeds. Wing designers must be masters of compromise. To fly fast, they must delay the formation of shock waves to the highest possible speed. And to fly far, they must reduce the drag to a minimum without reducing wing strength or stability. Logically, as has been seen, if we're to fly fast, we ought to lessen the thickness of the wing until it becomes razor thin. But in practice, such razor thin wings cannot be made strong enough to carry the loads they must bear. How can we, with a normally thick wing, obtain the effect of a thin wing? This we can do by sweeping back the wing. Let's see how sweepback affects the airflow over a wing. It's the speed of the air at right angles to a wing which matters. This is the speed which influences the formation of shock waves. The wing we see has an airspeed at right angles to it of 500 miles per hour in every case. But to keep this airspeed at 500 miles per hour as the wing is swept, the speed at which the wing is traveling forward increases. When the wing is swept at 45 degrees, its speed can be increased to 700 miles per hour without incurring any greater drag than on an unswept wing traveling at 500 miles per hour. Thus, when designing a wing for a given speed, these effects allow the designer to make a swept wing thicker than an unswept one without increasing its drag. He can choose between a thin, unswept wing or a thicker, swept one. The greater the sweep, the thicker he can make the wing. If we sweep our wings greatly, the span decreases, and in effect, we arrive at a rectangular planform with its shortest side forming the span. No one would think of using this inefficient shape. The reason for this is that as the span decreases, another form of drag called induced drag increases out of all proportion with a decrease in span. There are many variants of the short span wing. A typical example is the triangle wing, which one first meets on the juvenile paper dart. They are all handicapped by a high induced drag. I mentioned induced drag a moment ago. This is the air resistance which depends on the ratio of a wing's span to its chord. See how this type of drag arises. A wing lifts, in effect, because the air exerts a suction on its upper surface. But at the wing tips, air escapes round the end edges, reducing the lift at the tips and producing a trail of swirling air from each tip. These are the so-called tip vortices. Large diameter vortices greatly affect the flow round the short span wing. But the greater the wingspan, the less do the vortices affect the airflow, and the lower is the induced drag. So we see here the small span sparrow, flits only from wall to wall. It's the large span albatross that flies across vast oceans from continent to continent. Similarly, a long-range, high-speed aeroplane, whether bomber or transport, must have a large wingspan. But the highly swept wing suffers from the great fault that at or near the stall, just that speed or thereabouts for landing, the wing becomes unstable. The pilot has difficulty in controlling the aeroplane. How does this arise? And how can we cure it? Here in the wind tunnel, we see a straight wing with tufts of wool attached to its surface, which has its angle of incidence progressively increased. Looking down on the wing, we see that at small angles of incidence, the air flows evenly over it. The tufts lie flat against the surface and parallel with the airflow. As the angle of incidence is increased, the even airflow breaks down, and the wing begins to stall first over the inner section of the wing and causes the tufts to rise. As the stall spreads along the span, all the tufts become disturbed until the whole wing is in a stalled condition. On a swept-back wing, the airflow breaks down first at the wingtips, just the reverse of the straight wing. Here we see how the tufts at the wingtips rise first, and the area of disturbance grows as the stall spreads inwards. Wingtip stalling causes the wing to drop, and hence results in instability at the stall. The answer to the designer's dilemma is to have a large sweepback where the wing has to be relatively thick at the center near the fuselage, as the stresses here are highest, and here also provision has to be made to house engines and undercarriage. Outboard from this center section, wing stresses are less, the wing can be made thinner and the sweepback decreased. The outer portions of the wing have the least stresses, they can be made thinner still, and therefore have least sweepback and minimum tendency to wingtip stall. So by unassailable aerodynamical logic, we come to the crescent wing planform. which combines the aerodynamic and operational merits of the swept, the razor-thin, and the paper dart wings, while avoiding their shortcomings. There's yet another reason for using a crescent wing. When a straight swept wing is bent by an aircraft maneuver or a vertical gust, it twists, giving the aircraft a nose-up tendency which sharpens the maneuver. In bad cases, this restricts the speed at which it's safe to fly. But the crescent wing twists only slightly when bent and has good handling characteristics up to the highest speed required. Our complete wing of large span, and therefore low induced drag, has an excellent performance at altitude. So, after an exhaustive study of these aerodynamic, structural, and general design problems, the Handley Page Victor was born. The crescent wing is steeply swept at the roots to achieve high speeds, yet allowing depth enough to stow 4 sapphire jets and the 16 wheels of the sturdy undercarriage. Also, thanks to this shape, the main spar does not encroach on valuable storage space. It passes well forward of the load compartment. But towards the tips, where the wing can be thinner, the angle of the sweep decreases, thus reducing the danger of tip stalling and improving control at high speeds. Then again, the span of the Crescent can be great without paying the penalty of unnecessary wing area and weight. As the Handley Page Victor takes the air, we see a new shape rise in the sky. At all speeds near the ground, the crescent-winged aircraft controls easily enough to please the most exacting pilot. While at takeoff and landing, the attitude is normal enough to reassure the most conventional. These are important factors when pilot familiarization is considered. No small crescent-wing trainers are needed. Notice the dive brakes, which on the Victor control the glide path without any change of trim. Now the Victor comes into land, and one of its most important features comes into play. With hands off the controls, the pilot brings it in on the approach. It flattens out and lands without the pilot touching the controls, an amazing and almost unbelievable characteristic of this crescent-winged aircraft. How is this done? It's due to the effect of the ground. Here we see the aircraft on the approach, still some distance above the ground. The weight acting downwards is supported by the lift on the wings, together with a downwards lift on the tail to provide balance. As the aircraft approaches the ground, the lift distribution on a crescent wing changes and results in the center of the air pressure moving forwards, which in turn causes the nose to tilt up. At the same time, owing to the high tailplane position, the ground only causes a change of lift on the tailplane sufficient to give the appropriate rounding out of the aeroplane on landing. This process continues until the aircraft flattens out just at ground level and lands itself smoothly without movement of the elevator. The nose is gently lowered and the aeroplane brought to rest. Now, let us hear what Sir Frederick Handley Page has to say about it.
Well, in this film we have shown, and you have seen, how simple, unassailable aerodynamical logic leads to the use of the crescent wing, which combines, as no other wing form does, those aerodynamical qualities which give outstanding performance at high altitude, coupled with excellent control near the ground. Our near-sonic Victor is but the forerunner of the Crescent era. Our HP80 97 intercontinental jet airliner, a model of which you see here, will bring the advantages of the Crescent wing to civil aviation. With 120 passengers, it will cross the Atlantic 3 times a day at a direct operating cost of £14 per passenger. It owes its performance to the Crescent wing, which in our new aircraft will ensure that Britain's bombers and transports will fly fastest, farthest, and highest in the years to come.
The wonder of flight has puzzled mankind since prehistoric times, when nature first started to solve the problem of flight. After untold millions of years, nature evolved the earliest forms of flying creatures, such as the grotesque pterodactyl and the first feathered bird, the Archaeopteryx, which were flying before ever man roamed the face of the earth. Nature's development of flying creatures has taken many millions of years, and today we have the eagle with its slotted wingtip feathers for slow landing. But even nature failed to make wings strong enough to carry on the evolution to the high-speed flight of today. To mankind, in a mere 50 years, it was left to advance from the eagle's counterpart, the glider, by way of the stick and string biplane, Stressmen and designers think years ahead and evolve the aircraft of the future. In wind tunnels, technicians test models of aircraft yet unveiled. In the works, too, modern methods of construction have played their part. Machining of metal skins is only one of the new techniques in use today. All these have played their part in the latest development for high-speed, long-range flight, the Crescent wing. On airfields, the work of engineers, test pilots, and flight observers to the near-sonic Crescent-winged aircraft of today. Aircraft like the aptly named Victor, shielded by the sound barrier against the onslaught of fighters. How has this rapid advance taken place? Not by slow, natural evolution or the survival of the fittest, but by scientific research and practical development. In design offices, aerodynamicists